So, we consider the error analysis for direct methods. So, let us first give some examples to show that small errors can produce large deviations in the solution. So, let us consider the following example. Suppose say I am given a system of equations of the form 2x plus y equal to 2, 2x plus 1.01y equal to 2.01. It is immediate that this has the solution x is equal to half and y equal to 1. So, we can substitute x as half, that will give you 1, y is 1. So, this equation is satisfied. X is half, so it is 1 plus y is 1, so 1.01, that gives you 2.01. So, half comma 1 is the exact solution of the system of two equations that we have written down. If suppose I consider the following system, namely the first equation is as it is. I observe that there is a small change in the coefficient of x in the second equation. There is a small change in the second component of the right hand side vector. I would like to see what is the solution of this system, and I observe that this system has the solution given by x is equal to 5 and y is equal to minus 8. So, small changes in either the coefficient matrix or on the right hand side vector yield very large deviations in the solution of the system. In that case, we say that the system is ill conditioned. Namely, for when there are small deviations in the input resulting in large deviations in the final solution, we call the system to be an ill conditioned system. Let us consider another example. Suppose say the matrix A is minus 73, 78, 24, 92, 66, 25, minus 80, 37, 10. And if I compute the determinant of A, it turns out to be 1. There is a small change in this entry, say it is 92.01. The rest of the entries are as they are, there is no change. And if I compute the determinant of this, it turns out to be 2.08. This change is very, very small. 92 has been changed to 92.01, but the determinant value has changed from 1 to 2.08. Let us take the case when this entry 78 is changed to 78.01. The other entries remain as they are. And if I compute the determinant, then it turns out to be minus 28.20. And if I consider say the determinant with entries as minus 73, 78 and 24, 92, 66, 25, minus 80, 37, say I make a small change in this entry, then you observe that the determinant turns out to be minus 118.94. We have made only small changes in one of the entries in any one of the 3 rows in each of these cases that we have considered. But we observe that the value of the determinant A is such that there are large deviations from the value, namely determinant A equal to 1 for the given matrix A. So, small changes in any one of the entries in the matrix A, which is the coefficient matrix for a system, has resulted in large deviations in the determinant value. And therefore, we say that this matrix is ill conditioned. And therefore, if this matrix had been the coefficient matrix of a system of equations Ax is equal to B, if small changes occur due to round off errors in any one of its entries, then it is going to give large deviations in the solution of that system. And therefore, the system is going to be an ill conditioned system. Let us consider another example where I solve the system whose coefficient matrix has entries given by these, and I have to solve for the unknowns x, y, z, w, so that the right hand side vector is 32, 23, 33, 31, and I immediately observe that my solution is x is equal to 1, y equal to 1, z is equal to 1 and w equal to 1. So, you can simply verify 17, 25, 32, 12, 18, 23, 14, 23, 33, 12, 21 plus 10, 31. So, these are the solutions of this system of equations. Now, I would like to make a small change on the right hand side vector. See, due to some round off errors, the right hand side vector is say changed. So, I shall introduce those changes here. Suppose the right hand side vector changes to 32.1, then 23.9 or 22.9, 32.9 and 31.1, right. So, the first and the last entries, some increase is incorporated, and in the second and the third entries a small decrease is introduced. So, that all the entries in the right hand side vector are changed, and if you solve the resulting system, you will see that x turns out to be 6, y is minus 7.2 and z is 2.9 and w turns out to be minus 0.1, and you observe such large deviations in the solution of the system for very small changes on the entries in the right hand side vector, and therefore, the system is again an ill conditioned system. Because small changes result in large deviations in the output, and therefore, your final solution cannot be a reliable solution. Why does it happen? There are round off errors which are incorporated while carrying out the steps which are involved in the methods that we have discussed, namely in the direct methods that we have discussed. And due to these errors, the final solution turns out to be 1, which is such that there are large deviations in the solution from the actual solution, and therefore, the system is an ill conditioned system. So, we must know a priori whether the system is an ill conditioned system. Alright. So, we must have a knowledge of the magnitude of the error that is being incorporated at each step of our computation, and that is why we need to perform the error analysis for direct methods, and we shall see how we can obtain the magnitude of the error that is incorporated at each step from our discussions which follows. So, to discuss the errors in the numerical methods involving vectors, it is useful to introduce the concept of or ideas of norm of a vector. So, let us define what we mean by a norm of a vector. The norm that we are going to introduce generalizes the notion of magnitude, say, of R, of a real number or a complex number. So, the norm is a notion which generalizes the magnitude of a real number or a complex number. When we consider norm, we consider norm of a vector. So, it gives you the length or the magnitude of that vector. So, let us define what we mean by a norm of a vector. So, we introduce what are called vector norms. So, let us call the n-dimensional Euclidean space as V. Then on this set V, we introduce a norm. So, a norm is a function from V onto the set of non-negative reals. That obeys the following postulates. So, it satisfies the postulate that norm x is greater than 0 if x is different from 0. Where does x belong to? X belongs to Rn. So, if n is 3, then when we say x belongs to R3, then x has components x1, x2, x3. So, x is a vector in the 3-dimensional Euclidean space. That is what we mean. So, here x belongs to Rn. So, x will have components x1, x2, etc., xn. So, it has n components or it is an n tuple. So, it is a point in the n-dimensional Euclidean space. What does it satisfy? It satisfies the condition that norm of x is positive if x is different from 0. Secondly, norm lambda x is going to be mod lambda into norm x if lambda is a real number and x is in Rn. And thirdly, norm x plus y is less than or equal to norm x plus norm y. So, as we remarked, norm x generalizes the notion of absolute value for a real or a complex number. So, this non-negative quantity, norm x is positive. So, the non-negative quantity norm x where x belongs to Rn is a measure of the length of this vector x, or it is the magnitude of this vector x. The most commonly used norms are as follows. So, one can introduce the Euclidean norm, which we denote by norm x suffix 2. It is just a notation. What does that mean? It is sigma I is equal to 1 to n xi square whole to the power of half. And what is x? X has components x1, x2, etc., xn. I take a point having components x1, x2, x3 and then measure this length, which I call as r, then it is nothing but square root of x1 minus 0 the whole square plus x2 minus 0 the whole square plus x3 minus 0 the whole square, namely root of x1 square plus x2 square plus x3 square. That represents the length of this vector or the distance of the point P from the origin. This is extended. You consider all the components of the vector, square them, add them, take the square root, and that is denoted by norm x2. So, this represents the length of the vector x in Rn. Another commonly used norm is the L infinity norm. So, you denote that by norm x infinity. What is it? It is maximum of modulus of xi for I lying between 1 and n. So, what is norm? Norm is a function from V, that is Rn, onto set of non-negative real numbers. So, you will end up with a real number, that is the norm of x. Take an x in Rn, then norm x is a real number, which is a non-negative real number. And therefore, I must have a number here when I write down norm x infinity. What is it? Earlier I took it to be the distance of the point P from the origin, where the point P is in Rn. Now I take the norm as follows. What is it? It is maximum of the absolute value of the xi. So, I look at the vector x, which is given to me, and I look at all the components of vector x. Take the absolute value of each of these components. From among them, I see which is the maximum. I take that and I call that as norm x infinity. If I do that, then I have defined L infinity norm on V. Thirdly, I have what is called L1 norm. I denote it by norm x1. And what is it? It is sigma I is equal to 1 to n modulus of xi. So, in this case, what do? Given a vector x in Rn, I look at the components of that vector and consider the absolute value of each of these components. I add them all. That is what I have done. Sigma I is equal to 1 to n mod xi. So, I have a real number, and this is what I call as norm x1. So, given Rn and vectors x belonging to Rn, I can use any one of these definitions of norm on Rn and find out the magnitude of that vector x. Is it clear now? So, let us try to understand the notion of norm by taking the following set and trying to sketch that set in R2. A set of all x such that x belongs to R2, and I want the set to be such that it should consist of all those points x in R2. R2 is a plane. So, in R2 such that norm of x is strictly less than 1. Suppose I want to sketch this set, I call this as S, and I want to use the norm as the Euclidean norm. What is the set? So, if I use the Euclidean norm, then what do I want? I want all those members x in the two-dimensional plane such that x is now having components x1, x2. So, I want to use norm x2. By definition, it is root of x1 square plus x2 square. So, any typical x which is given to me having components x1, x2, then it will belong to this set if its distance from the origin is less than 1. So, what all those points which will satisfy this criterion will all lie within a unit disk in the two-dimensional plane. So, all those points within this circle where suppose this is x1 axis, this is x2 axis, this point will be 1 comma 0 and this is minus 1 0. This will be 0 1 and this will be 0 comma minus 1. So, this is what the set describes in R2 if I make use of the Euclidean norm. Let us use the L infinity norm for the same set. So, if I use L infinity norm, then in the Euclidean plane, which is a two-dimensional plane, I would like to mark all those points x such that norm x infinity must be less than 1. What is norm x infinity? It is the maximum of modulus of xi, and that must be less than 1. So, what are those points? They are going to be points which lie within this rectangle. So, x1, x2. So, this point is minus 1 comma minus 1 and this point is going to be 1 comma 1. So, 1 comma minus 1 and this will be minus 1 comma 1. So, all those points within this rectangle will belong to this set S when you use infinity norm. What about the third case? What if you use the L1 norm? So, you must have all those points in the two-dimensional plane such that the sum of the absolute value of the components of each of these vectors that you take must be less than 1, and therefore, in the two-dimensional plane you will have a set which consists of all those points which satisfy the condition. So, this will be 1 0 and this will be 0 1. So, if you use this norm and mark all the points which lie in this set S, so these are the points which lie within this rhombus. I hope how you compute norm 2 or norm infinity or norm 1. Maybe we can take some more examples so that we have a clear understanding of the notion of these norms. Suppose say I give you the following vectors, namely x has components 4, 4, minus 4, 4, and then y is another vector having components 0, 5, 5, and say v is a vector or w is a vector 0, 0, 0. So, I would like to find the norm of x if I use each of these definitions. So, I want to use norm 1, norm 2 and finally norm infinity for the vector x which is given to me. What is norm 1? If I use norm 1 to compute the L1 norm for the vector x, it is take the absolute value of each of the components and sum it up. So, it is 4 plus 4 plus modulus of minus 4 plus 4. So, that is going to be 16. What about norm 2 for this vector? It is going to be square root of 4 square plus 4 square plus 4 square plus 4 square, and therefore, that is going to give me the value as 8. What about norm infinity? Norm x infinity, it is the maximum of modulus of xi. So, it is the maximum of mod 4, mod 4, mod minus 4, mod 4. So, that is going to be 4. So, let us do the same thing with the vector y. So, the norm 1 is going to be the sum of the absolute values of its components. So, it is going to be 5 plus 5 plus 5, so 15. Norm 2 root of 5 square plus 5 square plus 5 square. So, root of 75, isn't it 25 plus 25 plus 25, and that is going to be 8.66. What about norm infinity for y? It is going to be maximum of modulus of 0, mod 5, mod 5, mod 5. So, that is going to be 5. Let us now take the same definitions of the norms for the vector w and compute each of these norms. So, for w it is going to be norm w1. So, it is the sum of the absolute values of the entries. So, it is 6. Norm 2, that is square root of 6 square plus 0 square, etc. So, 6. And then norm infinity, maximum of the absolute values of the entries, which is again 6. So, now we know, given a vector x in Rn for any value of n, we know how to compute the norm of that vector with respect to either the Euclidean norm or the L1 norm or the L infinity norm. So, when we solve the system of equations with direct methods, we come across a matrix also, namely the system is given by Ax is equal to b, where x and b are vectors and A is a square matrix. So, we should also have some knowledge about the matrix norm. So, let us introduce the notion of matrix norm that is associated with the vector norm.